I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
Imagine a world where electricity flows without resistance, power grids lose no energy, trains levitate silently above the tracks. This is the promise of high-temperature superconductors, or HTS. Scientists have dreamed of this since 1911, when Dutch physicist Heike Kamerlingh-Onnes discovered superconductivity. Superconductors are special materials. They allow electricity to move without losing any energy. Early superconductors only worked near absolute zero, which is extremely cold. Cooling them required expensive equipment and made them hard to use. Then, in the 1980s, scientists discovered high-temperature superconductors. These materials can superconduct at much higher temperatures. They only need liquid nitrogen to stay cold, which is much easier and cheaper than extreme cryogenic cooling. This discovery made real-world applications possible. High-temperature superconductors can carry huge currents with almost no resistance. Signals travel with very little distortion. They can even push away magnetic fields, a phenomenon called the Meissner effect. This allows trains to levitate or plasma to be contained in fusion reactors. Superconductors also support ultra-fast digital switching. Electrical signals can move near the speed of light, making advanced computing and real-time communications possible. The applications are exciting and wide-ranging. Superconducting power lines can transmit electricity with almost zero loss. Cities like Seoul and Essen are already testing them. Fusion reactors use HTS magnets to confine plasma at millions of degrees. Maglev trains use superconducting coils to float above tracks, moving faster, quieter, and more efficiently. Aerospace engineers are also exploring HTS motors for electric aircraft. They can reduce weight and save energy compared to conventional engines. High-temperature superconductors are key to quantum computing, too. Superconducting circuits form qubits, which keep delicate quantum states stable for complex calculations. Devices called squids detect tiny magnetic fields, helping medical imaging and materials research. MRI machines use superconducting magnets for higher resolution scans and faster, more comfortable imaging. Even satellites and defense systems can benefit from compact HTS magnets for high-power applications. But how do superconductors work? Ordinary superconductors follow BCS theory. Electrons pair up by exchanging vibrations in the crystal lattice. This allows them to move without resistance. High-temperature superconductors are more complex. Electrons interact in special ways beyond simple vibrations. They form strongly correlated systems with phenomena like spin fluctuations and charge waves. Their layered atomic structures like copper oxide planes and cuprates are essential. Adding extra atoms, called doping, introduces mobile charge carriers, helping electrons flow and creating superconductivity. There are many types of high-temperature superconductors, each with unique strengths and challenges. Cuprates, which are layered copper oxide compounds, offer the highest superconducting performance at ambient pressure, but they are brittle and difficult to shape into wires or cables, limiting some practical uses. REBCO tapes, made from rare earth barium copper oxide, are designed as coated conductors. They can carry very high electrical currents and are mechanically robust, making them ideal for power cables, magnets, and large-scale applications. Iron-based superconductors, including iron arsenide and iron selenide compounds, are slightly lower in temperature performance, but they are more flexible and easier to handle, allowing for higher current densities in real-world devices. Hydrogen-rich compounds, or hydrides, are remarkable because some of them can superconduct above 0 degrees Celsius, but they require extremely high pressures, limiting practical deployment for now. One of the most exciting recent breakthroughs comes from China's 2024 hybrid cuprate-iron superconductor. This material combines the high performance of cuprates with the mechanical stability of iron-based compounds. It achieves superconductivity in 86% of its volume at -73 degrees Celsius. Even more impressively, it does this under normal atmospheric pressure rather than needing extreme pressures like many other HTS materials. This combination of high performance, stability, and practicality makes it a major breakthrough for real-world applications in energy, transport, and advanced technology. Scientists are now racing toward room temperature superconductivity. In 2023, researchers at the University of Rochester achieved superconductivity at 21 degrees Celsius using nitrogen-doped lutetium hydride, showing that superconductivity at everyday conditions is physically possible. Controversies like LK99 remind us that careful validation is important. Challenges remain. HTS materials are expensive to produce. Even high-temperature superconductors still need cooling. Some materials, like cuprates, are fragile under stress. Researchers are exploring flexible and more robust alternatives. The future is thrilling. Imagine energy grids with zero loss, trains and aircraft moving without friction, quantum computers solving problems in seconds that ordinary computers would take millennia to handle. Governments and companies worldwide are investing heavily in this technology. Superconductivity is no longer just a lab curiosity. It is opening a new era of energy, transport, and computing. Every breakthrough brings us closer to a world where electricity flows freely, technology leaps forward, and the impossible becomes possible. Thanks for watching. Subscribe, follow, or visit idsth.com for more cutting-edge defense and tech insights. See you in the next one.